Hi there, welcome to another video. So in this video, we're going to use the stuff that we just proved in the last video. We're going to use the double and half angle formulas for sine and cosine and tangent. Are they hard? No, not really. I mean, they're really just some formulas we're just practicing right now. The two hardest things about this are figuring out sine and cosine of an angle that you don't know. We've done that many times. We've done that many times with a lot of the things like drawing the triangles and figuring out the quadrant. The other one is finding the quadrant for alpha over 2 or theta over 2 as the case may be. That can be a little bit challenging, but understand something about this. When they ask you to find all of this stuff, all of the double angle and half angle formulas for a trig function by giving you just one of them, if you can find sine and tangent, you can find the rest. If you know the quadrant, you can find the quadrant for alpha or theta over 2, and you have to be given the quadrant in order to do any of this stuff. So let's suppose that cosine theta equals 3/5. That would be given to you. Let's also suppose that they tell you theta is somewhere between 0 and pi over 2. So that would be quadrant 1. So they're telling you a few things here. They're telling you what cosine theta is, which allows you to understand the x and the r for the appropriate quadrant that you're in. They're also telling you that theta is between 0 and pi over 2, so theta is in quadrant 1. That says some important things. That says that sine, cosine, and tangent are all positive. Why? Because if the angle is in quadrant 1, all of those trig functions are positive in quadrant 1. Furthermore, when we get here to theta over 2, if theta is between 0 and pi over 2, then theta over 2 is half of that between 0 and pi over 4. It's also in quadrant 1. So when we get there, I'll show you that as well. But number one thing is we know cosine, we know it's in quadrant 1. Let's find sine and tangent so that we can work through all this stuff fairly quickly. So we're in quadrant 1. Now, being in quadrant 1, we can draw where that angle is and identify x and r from that. We've done it many times. We're just drawing a triangle, but because we're in quadrant 1, we know that x here and r here, x being positive would put you in quadrant 1 or 4, which is why cosine is positive in quadrants 1 and 4. But in our case, being in quadrant 1 says you're going to have an x of 3 and an r of 5 in quadrant 1. In order to find sine and tangent, you have to know what the y is. Because we're in quadrant 1, we know that y is positive, so sine and tangent will also be positive. We just have to use the Pythagorean theorem to do that. And doing just a little bit of work, we get that y equals plus or minus the square root of 16. 25 minus 9 is 16. Take a square root both sides. We've done it a few times here. We get plus or minus 4. This is the same exact logic as the plus and minus that we're going to get for all of the half angle formulas that you see on the board. We need to identify the quadrant to know what sign to pick. So if we have quadrant 1 identified for our angle, then y is positive in quadrant 1. That's why sine is positive in quadrant 1. It's also why tangent is positive, because both x and y are positive. That is the same logic we're going to use when we get to half angle formulas. So for us, we said, hey, cosine theta is 3 over 5. That's x over r. So x is 3, r is 5. We know it resides in quadrant 1. Let's just draw a triangle in quadrant 1 that represents what cosine is telling us. The x is 3 and the r is 5. Not a problem. The radius is 5. Finding y becomes a matter for Pythagorean theorem. We know quadrant 1 says y is positive in this whole quadrant. In fact, in quadrants 1 and 2, y is positive. So we're going to pick positive 4 and not negative. That right there allows us to find both sine and tangent of theta without even knowing what the angle is. So sine theta takes y over r. Tangent takes y over x. So we get 4/5 and we get 4/3 respectively. Now we're ready just to find the formulas for our double angle and half angle illustrations here that I'm using. So if we have sine of 2 theta, really what we're going to do is find the formula, write it down, and evaluate with the triangle that we just made. We already know cosine, we know sine, we know tangent. We're just going to be substituting. So sine of 2 theta, there's only one formula for the double angle sine formula. So sine of 2 theta is always equal to 2 sine theta cosine theta. It's the only one we really use a lot for sine of 2 theta. So sine of 2 theta equals this. The things not to do. It's really difficult to try to take whatever this angle is, double it, and try to figure out the trigonometry from that. Because that's what you'd have to do if you didn't have a formula. You'd have to go over here and say, hey, this is my theta. Now let's double that. I don't know what it is. Then let's figure out all the trigonometry from that. I don't know what that is. And then we can answer sine of 2 theta. That's a really hard problem. Instead, we say, let's use the formula that we've produced, that we've proven. And now, based on 2 theta being sort of simplified into 2 sine theta cosine theta, this is that theta. If we can just find sine of theta and cosine of theta, we will now know sine of 2 theta based on the formula. But we already know those things. So we can just write down 2 times sine theta is 4/5. This is the same angle as that. It's just we're multiplying by 2 and we had a formula that lets us do that. What you can't do, the other thing, is we can never pull out factors inside angles. We can't ever do that. We can't say, oh, this is just 2 sine theta. It's not the way that works. It's why we did the whole entire video last time on how this stuff actually does work. So sine of 2 theta is not just 2 times 4/5. In fact, it's 2 times sine theta, which is 4/5, times cosine theta, which is 3/5. And that's really all we can do. We can use a formula we've created based on some trig functions that we found to find something that's unknown. So sine of 2 theta in our case is, well, let's see, it'd be 24 over 25. 2 times 4 times 3 is 24 over 25. So we can find trig functions like sine of 2 theta by using formulas, but it's really hard to do directly. We almost always have to have some sort of an identity that lets us do it. So this is the way we walk through that. I suppose it's pretty cool. Not even knowing what the angle is, we can find sine of 2 times that angle. Let's go ahead and do cosine 2 theta. So cosine 2 theta does the same thing. It says pick one of the double angle formulas for cosine. Which one? It doesn't matter. Whichever one works easiest for you. So let's suppose that you only had to find that. Well, if you only had to find that, maybe you would use one of the functions for one of the equations for the double angle formula for cosine that was based on what you already had. For instance, if this is not making sense to you, for instance, you know that you're given cosine, right? You have a few choices for cosine 2 theta. You have cosine squared theta minus sine squared theta, but that involves both cosine and sine. You have 1 minus 2 sine squared theta, and you have 2 cosine squared theta minus 1. So look at what you're given. What you're given is cosine theta. If you hadn't have had to find any of this other stuff which involves sine and cosine, you could certainly take two cosine squared theta minus 1. That cosine theta is that cosine theta. So this would simply work out to 2 times, well, if cosine theta is 3/5, cosine squared theta is 3/5 squared minus 1. Just do that. That is based on the cosine that you already knew. You would not have had to find sine or tangent if you were only looking for that thing. So what this means for us is, hey, 3 squared is 9, 5 squared is 25. So 9 times 2 is 18/25 minus 1. So let's see, 18/25 minus 25/25. That would be 1. That's negative 7/25. So cosine 2 theta is negative 7/25. Now, what if you wanted to do it differently? Would it give you the same answer? Yes, of course. Having 3 options can save us some work like I showed you. You would not have had to do this if you were just finding cosine 2 theta. But let's say you wanted to use one of the more common ones. Not that it's super different, but you could have said cosine 2 theta equals cosine squared theta minus sine squared theta. Notice something right off the bat, that if you choose to use that formula for the double angle cosine, that you're going to need no sine. So that causes you a little bit extra work. It causes you to have to find that. Now, if you've already done it, it's not really a big deal to use. But if you hadn't, that would have been easier. So cosine squared theta says, take your cosine, that's 3/5, square it. Minus, take your sine, that's 4/5, square it. And subtract it. So 9/25 minus 16/25. Wait a minute. 9 minus 16 is negative 7. That's still negative 7/25. So any way you go, whether you want to use this one because you were given cosine, or this one because you're more comfortable with it, or if you want to use the other one would be 1 minus 2 sine squared theta. And if you had that, you might not want to use that because you were given cosine, but if you were given sine instead, you could certainly have used 1 minus 2 sine squared theta and got the same exact thing. So no matter which way you go with the double angle formulas, you're going to yield the same result. Just do whichever one looks easier to you. If you already have all of them, take your pick. It doesn't really matter. Let's go ahead and do our half angle formula for sine and half angle formula for cosine. This is where knowing the quadrant is very important. So I'm going to show you with the plus and minus, with our formula, and then at the very end, we'll determine which one to take, the positive or the negative. So sine of theta over 2, well, that's half of some other angle theta. And so when we use our formula, we're going to show this as plus or minus square root 1 minus cosine theta over 2. That's our formula. Hopefully you can look that up. You have this next to you, or maybe you've memorized it. Sine theta over 2 is plus or minus square root of 1 minus cosine theta over 2. Now, do you know cosine theta? Yes. Yes, it's right there. It's talking about that angle. This is why the half angle formulas are so nice. I have no idea what that is. I know where it is, though. We'll talk about that in a second. But I don't know what it is. But I do know what that is. So it relates it to something that I know by a formula. Again, what you can't do, you can't just say, let's pull out the 1/2. It does not work. That's why these identities exist, is to be able to change arguments. To be able to look at this under a different lens rather than theta over 2, because it's really difficult. It lets us do easier things with it. So we're going to go ahead and say, all right, this is plus or minus square root of 1 minus, because cosine theta is 3/5, we can substitute that. 1 minus 3/5 is 2/5. Two-fifths divided by 2 is 1/5. If we take that square root and apply it to both the numerator and denominator, we're going to get square root of 1, which is 1, and square root of 5, which is square root of 5. Now, we do oftentimes rationalize the denominator. You can probably do it in your head at this point, but you multiply by the square root of 5 over the square root of 5. One times the square root of 5 is a square root of 5. Square root of 5 times itself just gives you 5. So you have this choice to make right now. The sine theta over 2 is either positive or negative square root of 5 over 5. Now, which one? This is why I've been training you this whole time, to draw a picture of your triangle in the appropriate quadrant, because take a look at this. If this is theta, theta is in quadrant 1. We all know that. It even says that. Where's theta over 2? Really look at this. You could seriously do this. Cut this in half. This would be theta over 2. In what quadrant does that lie? Well, if I cut something in quadrant 1 in half, this is still in quadrant 1. So I know for sure that theta over 2 is in quadrant 1. Could you do it differently? Yes, you can. More algebraically, you can do it right from here. So I'm going to erase a little bit of this. But if you took this and divided everything by 2, why by 2? Because theta divided by 2 is theta over 2. That's fantastic. What do you do with inequalities when you divide your centerpiece, that middle inequality, the double inequality, by 2? Well, you divide the wings or the sides by 2 also. 0 divided by 2 is still 0. We never change inequalities when we divide by positives. Theta over 2 is exactly what we want it to be, theta over 2. And pi over 2 divided by 2 is pi over 4. Here's what this means. If your original angle is somewhere in quadrant 1, then half of that angle is somewhere in quadrant 1 between 0 and pi over 4. It's like even more in quadrant 1. It's totally in there. You can even see it. If this is somewhere in quadrant 1, then half of it is somewhere in half of quadrant 1, 0 to pi over 4. It's somewhere in there. All that to say that sine, cosine, and tangent will still be positive. If sine, cosine, and tangent are all positive in quadrant 1, this is still in quadrant 1. It's actually between 0 and pi over 4. That's definitely within quadrant 1, so theta over 2 is in quadrant 1. If sine's positive in quadrant 1, it's positive in there as well. So we would look at this and say, this is still in quadrant 1, take the positive. And now we would know for sure that sine of theta over 2 is positive square root 5 over 5 and not negative. You can't take both of them. You got to choose one depending on the quadrant. And that's why that's in your note that way, that with your half angle, positive and negative is determined by the quadrant of alpha over 2, or in this case, theta over 2. Let's go ahead and let's do cosine theta over 2. We're going to use a very similar formula. So with cosine theta over 2, it looks really similar, but that's a plus right there. But by doing that, because we can't just pull out a 1/2 or something, we've allowed ourselves to look at an easier angle, something that we already know. So 1 plus cosine theta would be 1 plus 3/5. Do some similar work. We're not subtracting, we're of course adding. So let's see, 5/5 plus 3/5 is 8/5. 8/5 divided by 2 is 4/5. If we take and apply the square root, we're going to get 2 over square root 5. And if we rationalize the same exact way, multiply by square root 5 over 5, square root 5, we're going to get 2 square root 5 over 5, because the square root times itself gives you that radicand. Now, which one do we pick, the positive or the negative? From all of our discussion, we know that our angle, our theta over 2 here, our angle is somewhere between 0 and pi over 4. That's what we showed mathematically. That's what we saw in our graph. But in either case, it's still in quadrant 1. This is still in quadrant 1, just half of that quadrant. What that means is sine was positive, but cosine and tangent are also positive. So we're going to pick the positive one because this angle here, alpha, theta over 2 in our case, is still in quadrant 1. I really hope that's making sense, that if theta is in quadrant 1, half of theta, or theta over 2, is still in quadrant 1. That's not always the case. So if you have something in quadrant, let's say 3, half of that angle is not necessarily in quadrant 3 anymore. It's probably in quadrant 2. but we'll take a look at that. So we want it, generally I do it this way with our original definition of where the angle is to find out where half of that is. It's probably the easiest way instead of drawing pictures. It's nicest to do that algebraically. Now let's go ahead, let's move on to our tangent. So we're going to do tangent of double angle and tangent of a half of an angle. So with tangent of 2 theta, we're really just looking at the formula, and our formula tells us that we're going to take and do 2 tangent theta over 1 minus tangent squared theta. And thankfully we know those things. We spent some time to figure out tangent. So tangent theta is 4/3. We're just going to substitute. So 2 times 4/3 gives us 8/3. Over 1 minus 16/9. That's 4/3 squared. So 1 minus 16/9, my goodness, that would be 9/9 minus 16/9. That looks like negative 7/9. If we multiply by a common denominator, or the LCD, that's going to give us, let's see, 9 simplifies with 3, giving us 3. Nine simplifies here, giving us negative 7. So we get 24 over negative 7. You'll also notice something about this, that with your double angle formulas, the signs of them, not sine, but signs like positive, negative, are taking care of themselves. That's really interesting because half angle doesn't do that. Double angle does. You see, tangent is positive in quadrant 1. What's twice of something in quadrant 1? Something in quadrant 2. Well, from 0 to pi over 2. So something generally in quadrant 2. So if we double that, any angle that relies, where double of it would be in quadrant 2, that negative sign will show up. So double of this angle would be in quadrant 2. It says tangent is negative in quadrant 2, and that shows up. Cosine is negative in quadrant 2. That shows up. Sine is positive in quadrant 2. That shows up as well. Just be careful to not make some assumptions. If you have a very small angle and you double it, it's not necessarily in quadrant 2. So sometimes you have positive, sometimes you have negative for cosine and tangent. What I'm telling you is that the signs will take care of themselves. Do not worry about the signs for double angle. They will work themselves out. It's the half angle ones, and you see it in the formula. Those are the ones that you have to worry about. So let's wrap this up with tangent of theta over 2. We have a formula for it. We're going to use the formula. We'll determine the sign in just a little bit. So tangent of theta over 2 says we're going to take plus or minus the square root of 1 minus cosine theta over 1 plus cosine theta. I suppose I've memorized it just by looking here and here. I know that tangent is sine over cosine, so I know that sine is going to be this minus and cosine is going to give us that plus. So that's why I memorized the formula as the sine over the cosine. Now we just plug in what cosine theta is. Because we already know it's 3/5, we just substitute that. So 1 minus 3/5 is 2/5 over 1 plus 3/5 is 8/5. Thankfully, those denominators cancel. We get 1/4. 2 over 8 is 1/4. Also, thankfully, that simplifies. Square root of 1 gives us 1, square root of 4 gives us 2, so we're going to get plus or minus 1/2. Now it's up to us to determine which one of those we take. Do we take the positive or the negative? You look at your quadrant. Because theta over 2 is somewhere between 0 and pi over 4. That's what that says. It literally says that. 0 to pi over 4 is still in quadrant 1. Tangent's positive in quadrant 1. You want to take the positive version. So tangent of theta over 2 is 1/2. These can take a lot of time. Obviously, I'm walking you through these verbally, so it's taking us a little bit longer. But in general, this is the way you go through it. You figure out your trig functions first if you're required to find all of these pieces. If not, maybe just find the ones that you actually need. So like if we were working on a long problem, they wanted to know what cosine theta over 2 is. Cosine theta over 2 has nothing to do with sine or tangent. You would not have to find it. We would just need to know what quadrant we lie in, what half of the quadrant is, then you just have one formula to use, and that's pretty nice. I'm going to come back with one more example of an angle that's not in quadrant 1. Then we'll go through some identities and do some equations. Let's keep on going. So we have another one, which at first glance is kind of awkward because you have cosecant. Cosecant, this has to do with cosecant. What in the world do we do? And then you have cosine theta is negative or less than 0. This is what they're trying to tell you with this. They're trying to give you sine and tell you a quadrant. So in order to find a quadrant, you need to know the value or sign of two different trig functions. So you need to know whether two different trig functions are both positive, both negative, or one's positive, one's negative. That will determine the quadrant for you. So that's what they're really trying to show you here. But it's kind of wrapped up in some stuff. So if you're given a cosecant, but everything you have to deal with is in sines and cosines, change it. If cosecant theta equals negative square root 5, then sine theta is the reciprocal. Sine theta has to be negative 1 over square root 5. If we rationalize, that's going to be negative square root 5 over 5. So what have they just told you here? They've told you that sine is negative. Furthermore, sine of theta is negative square root 5 over 5. They've also told you that cosine is negative. Cosine is less than 0. So where is both sine and cosine negative? Well, in quadrant 1, sine's positive, so that's off the table. In quadrant 2, sine's positive, that's off the table. In quadrant 4, cosine's positive, sine's negative. But in quadrant 3, both sine and cosine are negative. So what they're telling you, all hidden in this, is that cosine's negative, sine's negative. The only place it happens is quadrant 3. So what they're telling you is that your angle, theta, is somewhere in quadrant 3. However, don't just write quadrant 3. While that's important, in order to deal with some of this, the half angle, it's very, very useful to say, hey, if we're in quadrant 3, then our angle is somewhere between pi and 3 pi over 2. Specifically, it's not actually equal to there. It's somewhere between there. That is what quadrant 3 is, from pi to 3 pi over 2. So we know we're somewhere in that quadrant because sine and cosine are both negative. Now, because we know that, we can write this or draw this picture of this angle really clearly. So with our sine theta being negative square root 5 over 5, you could have done it here, might have been a little bit easier even, to consider this to be y and this to be r. Remember that we want our x's and y's to be negative, but we do want our r's to be positive. So wherever you go from here, whether this is y and this is r, or this is y and this is r, you'll get the same proportion for x. So what we want to do is write this as negative 1 for y, but square root 5 for r. Now, what if you had chosen negative square root 5 for y and positive 5 for r? While your x would be different, the proportions of cosine and tangent, they would not be different. So it doesn't really matter. I'm using this because I like the 1. So either one of these, it doesn't matter. Your cosine and tangent will come out the same. Either way you go. So not to worry about that. So I'm picking negative 1 for y and square root 5 for r. Again, you want your y to be negative. That it is. Your r to be positive. It is, giving us the sign of theta being a negative. Negative 1 over square root 5 or negative square root 5 over 5. From there, we've got to find the x. So we're going to do that. We'll use Pythagorean theorem and find the x. So we'd have x squared plus negative 1 squared equals square root 5 squared. We do just a little bit of simplification here. Square root of 5 squared is 5. If we subtract the 1, x squared is 4. Let's take a square root. Now, which one do you pick? That's where your quadrant comes in. So if we're in quadrant 2, we've drawn this picture, we can see it. We can literally see that x has to be negative there. You have to pick -2 and not +2. Now that we've done that, we can find our cosine and we can find our tangent. It had told us cosine's negative. Oh, we're seeing that now. -2 would give us a negative cosine here because r is positive, so that we know, if I write the negative, that cosine's negative, tangent's positive. So let's go ahead and find cosine and tangent of theta. Cosine says take your x over your r, so we have -2 over square root 5. Tangent says take your y over your x, so it's -1 over -2. And we can simplify that a little bit. Yeah, we really should rationalize that. So we should get -2 square root 5 over 5, and we should get +1/2. Now that we've done that, we're ready to go and find all of our double angles because we have sine, we've got cosine, we've got tangent, and our half angles because we have sine, cosine, tangent of whatever that angle is, and we know that angle is in quadrant 3, which will allow us to figure out what half of the angle is and then the sine of that angle. So we'll come back and we'll do that. All right, so let's get to it. Now that we've found sine, cosine, and tangent for whatever angle we've been given, let's find the rest of our double angle and half angle formulas. So let's take a look at sine of 2 theta. Since there's only one double angle formula for sine, we really have to use 2 sine theta cosine theta. Again, you can't just pull the 2 out. The only way to change arguments of a trig function is really to use an identity like the formulas you've been given. So I always write out the formulas instead of just doing them in my head or writing down what the fractions are for sine theta and cosine theta, just so I can memorize them. I'm used to them, and I can follow what's really happening. So sine of 2 theta equals 2 sine theta cosine theta. I've written it out, and now it's really easy for me to look at what sine theta is as -square root 5 over 5, and cosine theta as -2 square root 5 over 5. So I'm going to write that down. So we have, let's see, 2 times -square root 5 times -2 square root 5 over 5 times 5. So it looks like we've got +4 times 5 over 25. We multiply everything together. This times this gives us 5, that gives us 4, so we're going to have 20 over 25. So if we simplify that, sine of 2 theta equals 4/5. Now, what do you do with cosine 2 theta? You have 3 options. So if we want to use a double angle formula, cosine squared minus sine squared theta is pretty common to use. None of them are super difficult, but it does depend on what you've been given as to maybe make it easier. So if you were just given sine theta, and you wanted to find cosine 2 theta, you wouldn't have to do any work if you use the one identity that's 1 minus 2 sine squared theta. You can just plug that right in there, square it, take 1 minus 2 times that, and you'd be done. Whatever way you want to go about it, sometimes these different formulas are more appropriate depending on what you've been given. So I'm going to do both. I'm going to do the cosine squared theta minus sine squared theta. Now, it's not all that hard, but keep in mind that we had to actually find cosine theta in order to make that work. So this will be negative 2 square root 5 over 5 squared. Minus negative square root 5 over 5 squared. What that's going to give us is positive 4 times 5, so that's 20 over 25, minus this will give us positive 5 over 25. And what that means is that cosine 2 theta is positive 15 over 25, or just 3/5. Now, I said sometimes it's easier depending on what you've been given. So if we didn't want to have to spend the time to find cosine theta and all we were looking for was cosine 2 theta, we might have used a different identity. We might have used 1 minus 2 sine squared theta. Now, does it still give us the same answer? Well, let's find out. If we did that, notice we've been given sine theta. It wouldn't have been all that hard to find. So that's 1 minus 2 times negative square root 5 over 5. That's sine theta. It's quantity squared. Well, that's going to give us positive 5 over 25. Times 2, that would be positive 10 over 25. So 25 over 25 minus 10 over 25 gives us 15 over 25. That's exactly what we get there. Doesn't matter which formula you use, but sometimes one of the formulas is a little bit more nicely suited to what you've been given. So in this case, you could have just used this formula and not had to find the cosine for that. So either way you go, you're going to get the same thing though, so it's not a huge deal. Let's move on and go ahead and do our half angle formulas. Maybe before you start your half angle formulas, it might be a good idea to figure out where this angle actually is. So the best way that I found to do this is draw your picture, determine your quadrant, but then take a look at the inequality version of that. If you divide everything by 2, it will show you where theta over 2, your half angle, is. So we're going to do that. So we know if we're in quadrant 3, we're between pi and 3 pi over 2. If we divide that by 2, I guess say quadrant 2, we're in quadrant 3. So if we divide that by 2, this says that if your original angle is in quadrant 3 from pi to 3 pi over 2, and you cut that angle in half, where are you going to be? Well, pi divided by 2 is pi over 2. 3 pi over 2 divided by 2 is 3 pi over 4. You're going to be somewhere between pi over 2 and 3 pi over 4. That's what that says. So by writing your quadrant in inequality form, finding half an angle is not all that bad. Just divide everything by 2. It says you are now between pi over 2 and 3 pi over 4. You are in quadrant 2 now. So this angle, half of an angle, changes from quadrant 3 to quadrant 2. Now that's really important because we know a few things about quadrant 2. We know that sine is positive, we know that cosine is negative, we know that tangent is negative. So when we get to our formulas right now, we'll know the appropriate sign to take. So let's take a look at sine of theta over 2. We know that sine of theta over 2 says you're going to take plus or minus 1 minus cosine theta all over 2. We know what cosine theta is. We worked hard to find that. That's negative 2 square root 5 over 5. It's pretty important to get the signs right. So we know we have 1 minus, but you do have that as a negative. So cosine theta is negative. Be careful, that's a really common mistake to make. And now we're just going to simplify this. So 1 minus negative 2 square root 5 over 5 is positive. So 1 plus 2 square root 5 over 5. All over 2. If we find a common denominator, that would be 5 over 5. So 5 plus 2 square root 5 all over 5, and then over 2. I'm going to write that out for you. When you have this and you have a fraction divided by a number, take and multiply these denominators. So you have 5 plus 2 square root 5 over 5 over 2. If you reciprocate and multiply, the 5 and the 2 end up getting multiplied together. So you're going to have 5 plus 2 square root 5 over 10. Now that's really nasty. So what do? You leave it. There's nothing you can do to actually simplify that and get away from the exactness of the answer. We don't really want to approximate this with decimals. We want to leave that as exact. The only thing we have to really determine is what to do to take the positive or the negative. So we go back and we look at where our angle theta over 2 actually lies. The original theta was in quadrant 3. We cut that angle in half. We're now in quadrant 2. So in quadrant 2, sine is positive. Sine is positive in 1 and 2. So quadrant 2 says, hey, this angle is positive. Take the positive version of this. We're just going to erase that. And we know that sine of theta over 2 is positive square root 5 plus 2 square root 5 over 10. It's ugly. You could approximate it, but leave it as an exact. Let's go ahead and move on and do cosine of theta over 2. So cosine of theta over 2 is very, very similar, except you add instead of subtract. So 1 plus cosine theta over 2, you're seeing I'm still writing out the original formula before I start to substitute in some of these values that we know. We know that cosine theta is negative 2 square root 5, so we'll have 1 minus 2 square root 5 over 5. All over 2. So we find a common denominator again. 1 over 1, or 1 minus 2 square root 5 over 5, I should say. You can write this as 5 over 5. So 5 minus 2 square root 5 over 5. All over 2. We're going to do the same thing, that whole multiply by the reciprocal or multiply your denominators. We're going to get plus or minus square root 5 minus 2 square root 5 over 10. All that's left to do now is determine whether that's positive or negative. So we take a look back at our quadrant. We say that theta over 2 is in quadrant 2. We've already determined that by cutting this in half. So theta became theta over 2, pi became pi over 2, 3 pi over 2 became 3 pi over 4. We're in quadrant 2. Let's see, sine's positive in quadrants 1 and 2. Cosine is negative in quadrant 2. Positive in 1, negative in 2. So if cosine is negative in quadrant 2, where that angle is, then we're going to take the negative version of that square root. So cosine theta over 2 equals negative square root 5 minus 2 square root 5 over 10. It's a lot of work to do as far as the simplification goes some of the times, but honestly, we're just following the formulas. The biggest thing that I said at the beginning is the quadrant. Determine your trig functions in the appropriate quadrant, and then determine the quadrant of theta over 2. All right, let's go ahead and do tangent of 2 theta, the double angle formula for tangent. We've got a couple ways to do this. So I didn't show this on the last example, but I really want you to see it now. The first way we do this is with our original formula. So tangent of 2 theta gives us 2 tangent theta over 1 minus tangent squared theta. Now, because we spent some time to find tangent theta, this is not a big deal. Tangent theta is just 1/2. So we're going to plug in 1/2 here. Of course, we'll square that on the denominator. 2 times 1/2, that is tangent theta for the appropriate angle in the correct quadrant. 2 times tangent theta is 2 times 1/2 over 1 minus tangent squared theta, which is 1/2 squared. 2 times 1/2 is just 1 over 1 minus 1/4. So 1 minus 1/4 is 3/4, or this whole thing, 1 divided by 3/4 is 4/3. And so it tells us tangent of 2 theta is just 4/3. Now, could you have done that differently? Yeah, you could. If you remember that tangent equals sine over cosine. Well, what that means is that tangent of 2 theta should equal sine of 2 theta over cosine of 2 theta. Tangent always equals sine over cosine for whatever the angle is. So this would equal sine of 2 theta over cosine of 2 theta. But wait a minute. Sine of 2 theta is there. Cosine of 2 theta is there. So if you want to do this a different way, if you've already found sine of 2 theta, you've already found cosine of 2 theta, just take sine divided by cosine. Simplified, we get 4/5 over 3/5. 20 over 25 simplifies to 4/5. So 4/5 over 3/5. If you multiply by the reciprocal there, so 4/5 times 5/3, the 5s are going to cancel. You are going to get exactly 4/3. And that would just be taking sine over cosine. Do it a number of ways. Any way is right as long as you're using an appropriate identity that gives you what you're looking for. There's oftentimes many ways to do it. Okay, so let's take a look at tangent of theta over 2, the half angle formula for tangent. What we're going to do is basically take a look at this formula, and the 2's cancel. So tangent is always a sine over cosine idea. That's where it comes from. And so we're going to take square root plus or minus square root of 1 minus cosine theta over 1 plus cosine theta. Cosine theta is negative 2 square root 5 over 5. So we're going to put that in both places. So 1 minus a negative, it's going to give us 1 plus 2 square root 5 over 5, divided by 1 minus 2 square root 5 over 5. With our common denominator of 5 there, you can do a couple things. You could find a common denominator here and here, or you could multiply both the numerator and denominator by 5. But if you do that, do not forget that you have to distribute to that 1. I'm going to show you that right now. But either way you go, you can put this as 1 fraction over 1 fraction, or you can multiply by the LCD as long as you distribute here and here. So 5 plus 2 square root 5 over 5 minus 2 square root 5. The 5's cancel in the second fraction. Now, as far as simplifying, there is technically one more thing you do. You could multiply by the conjugate of the denominator and make this a little bit nicer. So we could take some time to do that. Depending on who your teacher is or what you're working on, they might or might not do that. So I'm actually not going to. You could rationalize and make it a little bit simpler, but in our case right now, we just have to determine whether we take the positive or the negative. So we look back at our theta over 2. Theta over 2 is in quadrant 2. Well, what's tangent in quadrant 2? Tangent is negative, so we're going to take the negative square root of that. And that about does it for our double and half angle formulas, just working through some of the basics. What I'm going to do now is show you why you might want to know this for some very awkward angles to get exact solutions without having to approximate. Then we'll talk about 2 identities, we'll talk about 2 equations, and then we'll be done. All right, so we got a couple examples that illustrate that sometimes these identities, these formulas, help us to find exact answers of angles that are not on your unit circle. So this is quite valuable if you have to find an exact answer. Like cosine of 22.5 degrees. That's not on your unit circle. So here's the thought process. Could you use either a double angle or a half angle formula to rewrite this as a better angle, or at least one that's on a unit circle. So I might think 22.5 looks like an angle that's cut in half. It actually looks like half of 45 degrees. So wait a minute, maybe I could write this as half of 45 degrees instead of 22.5. So if I write this as cosine of 45 over 2, notice 45 over 2, that's still 22.5 degrees. But if I write this as 45 over 2 degrees, well, that's a half angle formula. That's something that we can use because when we have an angle over 2, well, our formula says that we can take and use this angle in that formula. Remember that the half angle says plus or minus square root of 1 plus cosine theta over 2. The only question is, what is your theta? Now, we've been doing a lot of examples, but if you remember, it was theta over 2. Here's why the half angle formula is so nice. If you can write this as an angle over 2, you get to use that angle over there. Cosine of 45 degrees is really nice for us to use at square root 2 over 2. But this is the reason why we'd want to use this sometimes, is so that you can get away from doing this and say, hey, I can use a half angle formula and really think of it as 45 degrees because of that formula. So we're going to say this is plus or minus square root of 1 plus cosine 45 degrees over 2. That's much easier, or at least possible, to find an exact answer. That one's not so much, because 22.5 degrees is on a unit circle. Here we go, hey, cosine 45 degrees, go to my unit circle, looks like square root 2 over 2. One plus square root 2 over 2. That would be 2 over 2 plus square root 2 over 2. So that's 2 plus square root 2 over 2. So common denominator here. You could also multiply both the numerator and denominator by 2, and as long as you distribute, just be sure that you're doing that. And you could get 2 plus square root 2 over 4. We're going to actually get the same exact thing here. We're going to get 2 plus square root 2, 2 divided by 2, 2 plus square root 2 over 2 divided by 2. Multiply your denominators. Multiply by the reciprocal multiplies your denominators. So either way we go about it, whether you want to do it that way or whether you want to multiply both the numerator and denominator by the LCD and distribute 2's cancel here, over 4, you get the same exact thing. The only thing that's left for us is to determine whether that's positive or negative. So you have to think back to your angle. Now, because we're given a specific angle, we're given 22.5 degrees. Where is that? Well, that's in quadrant 1. Or where's 45 over 2? Wait a minute, that is 22.5 degrees. That's in quadrant 1. Think about cosine in quadrant 1. Cosine in quadrant 1 is positive. So take the positive and you're done. So that's one way that we can use these half angle formulas to find an exact answer, not just an approximation, but an exact answer for an angle that we don't really have on a unit circle. We're going to do the same thing with tangent of 9 pi over 8. But there is one thing about this I want you to notice. That angle is outside of the first period of tangent. So tangent goes from 0 to pi. That's its first period. 9 pi over 8 is just outside that. Anytime that happens, like if you saw 5 pi over 2 inside of sine or cosine, you might want to put this on the first period. So we can always do this by subtracting or adding any number of periods to this. Like 9 pi over 8, I'm probably thinking, let's subtract pi. Why? Because it moves it from quadrant 3 into quadrant 1. It's a little bit nicer to deal with. Even though tangent is positive in both of those, it's just a little bit nicer. So what I'm saying is that anything outside of the first period of your trig function, you can always subtract some periods to get it into one period. So since the period of tangent is pi, let's subtract pi. And what that means is that if we find tangent of pi over 8, it's going to be identical to tangent of 9 pi over 8. And that's nice. It's a little easier to deal with. But then comes the hiccup, and you go, wait a minute, that's not on my unit circle either. I know it's in quadrant 1. Think about why that is. If you cut pi into 8 pieces, so 1, 2, 3, 4, and 5, 6, 7, 8, and you go to one of them, you are in quadrant 1. So tangent's going to be positive. So when we deal with our formula, our half angle formula, which you're going to get in a little bit, we are going to take the positive square root. But pi over 8's not on anything. So how in the world could you think about that? Well, pi over 8 looks like half of some other angle. What an angle? Pi over 4. Pi over 8 is half of pi over 4. If you took pi over 4 and divided by 2, you get pi over 8. Therefore, pi over 8 is a half of an angle of that. And that is what we get to use in our formula. That's what makes it so nice. So we're going to write out our formula. Just keep in mind, that angle, that theta, is this thing. We're really kind of tricking the problem. We're thinking of this as half of some other angle. It's that angle that you get to use, which is what makes this all possible anyway. So we're going to use pi over 4. We've actually done that, haven't we? Because cosine of 45 degrees and cosine of pi over 4 is 45 degrees. We're going to get that square root 2 over 2 again. In this case, I would certainly multiply both the numerator and denominator by 2, getting rid of that LCD. As long as we distribute. So 2 times 1 gives us 2. Square root 2 over 2 times 2 is just square root 2. Something very similar happens here. We get 2 plus square root 2. We could rationalize the denominator, multiply both of these by 2 minus square root 2 over 2 minus square root 2 and distribute. That would work. But in our case, I'm not going to do that. It's just a little bit more than I want to spend time on right now. What I will do, though, is look at the sign. So because tangent of pi over 4 over 2, or pi over 8, we're looking at pi over 8, that gives you your quadrant. That's quadrant 1. Tangent's positive in quadrant 1. We'll take just the positive version of that square root. You never leave both positive and negative for these half angle formulas. So I hope that's made sense. We're going to come back with 2 very fast identities. Then we'll do 3 equations pretty quickly, and then we'll be done. Okay, we're about to go through 2 identities because it's really good to remember these things. You deal with identities many, many times, especially in calculus 2, when we deal with a lot of trigonometry in some things called integrals. So we're going to get there. So right now we're going to refresh just on how proving identities works. Remember that what we want to do is start on like the harder side. And there's lots of different things that we deal with. But one of the main concepts was look at the harder side, look to see if there are any identities right there. If there are, take care of it. If there's not, see if everything's in sines and cosines. Make one fraction maybe. Factor if you can. And so let's go ahead, let's start with this guy. Cosine to the 4th theta minus sine to the 4th theta equals cosine of 2 theta. I think the harder side is this side, so I'm going to start there. And I'm looking at that. That's, wow, well there's not more than one fraction, so I can't make everything one fraction. I don't see an identity that's right there popping up at me. Everything's in sines and cosines. I might try to factor this because I'm seeing this as kind of like it's kind of like a difference of squares. It's something squared, or cosine squared minus sine squared. So it's like a difference of squares. Maybe I'll write it like that. Now that we've written this as a difference of squares can factor. Do you remember that? It's very similar to x squared minus y squared, and you write this as x minus y and x plus y. That's a difference of squares factoring. We're about to do exactly the same thing. It's just that we have this squared minus this squared. First thing squared minus second thing squared. How it works, we take cosine squared theta minus sine squared theta times cosine squared theta plus sine squared theta. I'm really hoping that you see the similarity here. It's just a difference of squares. This stuff is first thing squared minus second thing squared, just like x squared minus y squared. We just take our cosine squared minus sine squared, cosine squared plus sine squared as a product of one another. So after that, what do? Don't factor again. That's what you don't do. Don't factor again. You see, the thing about proving identities is we want to make sure that we're always checking for a known identity, like after everything that we do. So I don't want to start going and factoring that. That doesn't factor. But I certainly don't want to factor that. The reason why is because if we're checking for identities, oh, this is a beautiful one. Cosine squared plus sine squared theta is 1. That's the Pythagorean identity. So this is just 1. What about this one? Cosine squared theta minus sine squared theta. If we have our identity sheet next to us, or we're really used to the double angle identities, this is one of the double angle identities formulas for cosine. So cosine 2 theta, there was 3 double angle formulas for cosine. The first one was exactly what we see here. So that's a big point. That these formulas, they're not just one way, they go both ways. So if you have cosine 2 theta, sure, you could write it as cosine squared theta minus sine squared theta. But on the other hand, if you have cosine squared theta minus sine squared theta, like that, you could also write that as cosine 2 theta. Now that's perfect, because cosine 2 theta times 1 is cosine 2 theta. And we've just started with the hard side. We've done some factoring, we used some identities, and we've ended with what we wanted to prove. So that states it. And that's it. So we've just proven that identity. How about the next one? This is super similar. Very, very similar, because we're going to use the same exact formula. We see right here that that is a difference of squares. But if you notice, it's also this right here. So you go, well, wait a minute. That doesn't have 2 theta in it. That just has theta in it. Yeah, but we can do the same thing. So keep in mind what happens. Cosine 2 theta equals cosine squared theta minus sine squared theta. Here's what this really says. It says cosine squared theta minus sine squared theta is, you can write this thing as cosine of 2 times whatever that angle is. Cosine squared theta minus sine squared theta is cosine of 2 times whatever that angle is, as long as they're the same, which they are. So what about that? This can be written as cosine of 2 times whatever that angle is, which is 2 theta. Well, wait a second. We started on the hard side. We saw an identity right off the bat. We've used it. And now cosine of 2 times 2 theta, 2 times 2 theta is 4 theta. And that's exactly what we're trying to prove. That proves our identity. So about these identities, now that we have more tricks in our bag, it actually makes things a lot easier. So when we see an identity right off the bat, you can go for it. A lot of times there's some factoring involved, but keep with the same kind of core features of how to solve identities. Number one, if you have fractions, get one fraction. Use known identities anytime you can, and immediately after you do something, check for an identity there. Factoring is always a good tool if you're getting stuck. And then remember that identities are not just one-way streets. They're two-way streets. We can go forward, we can go backwards on them. It oftentimes helps with a lot of things that we deal with. Last little bit, we've got 3 equations that we're going to solve. They're going to go fairly quickly, but you're going to notice something about this. There's an appropriate choice for some of these double angle formulas that you have to make. So we're going to take a look firstly at cosine of 2 theta plus 6 sine squared theta equals 4. When we deal with these, oftentimes the worst part of this is the double angle. You see that doesn't play along very nicely with things that aren't double angle. And so typically the way these equations work is find the double angle, use the appropriate formula to get away from that double angle, and then almost always we have some sort of a factoring involved. So cosine 2 theta, I don't really like it. The sine squared theta, I don't really want to change that. I don't want to change that into a double angle because they're a little bit harder to deal with. So maybe I'm looking here and I change that out of a double angle. Now, which one do we use? Because we know that we have 3 different formulas for cosine 2 theta. This kind of goes back to an identity idea. Look at what else you have. Like, what else is outside of that? If you have a choice on what you make that, what's the best choice? Would you want to see more cosines or would you want to see more sines? Here's a sine squared. So wait a minute. If I use the cosine squared, sine squared, that might not cancel that all the way, and then I have another cosine squared. That's growing larger, not getting better. If I use the 1 minus 2 sine squared, oh, well, I could combine some like terms. So that would be a great choice. Let's use that one. Let's use the one that identifies with the trig function we already have. So we've taken a look at it. We said, I really don't like double angles. Let's change that first, but I'm going to use the appropriate one that matches what I already have. 1 minus 2 sine squared theta. It looks like a good choice because I already had some sine squared thetas up there. Now we can combine some like terms. And once we do, we see 1 plus 4 sine squared theta. Just combine like terms. Hey, there's only one trig function left. If we isolate that, we can take a square root both sides. So we'll subtract 1 and divide by 4. So we work all the way down to sine squared theta equals positive 3/4. Remember that sine squared theta means sine theta squared. So you have your variable inside of a function to a second power. The whole thing's to a second power. You can take a square root, but if you do it, you've got to remember to take it on both sides and you have to put that plus and minus. We see that we get this sine theta equals plus or minus square root 3/2. Now, square root 3/2 is a great number. It's on our unit circle. But just remember that you have to find out all the solutions on 0 to 2 pi that equal either positive square root 3/2 or negative. So sometimes I'll do this. I'll write this out as 2 different equations. Sine theta equals positive square root 3/2 and sine theta equals negative square root 3/2, just so I don't get confused. And the reason why I'm doing that is hopefully you can see that on 0 to 2 pi, you're going to have 2 angles that give you this and 2 angles that give you that. There's going to be 4 angles here. So we walk through this. We think about where is sine theta equal to positive square root 3/2? That would be quadrant 1 and quadrant 2. Sine's positive in 1 and 2. Where would sine theta equal negative square root 3/2? That's quadrants 3 and 4. Sine's negative in 3 and 4. So we're going to get theta equals pi over 3 and 2 pi over 3. So where's sine theta equal negative square root 3/2? That's in quadrants 3 and 4. So let's see, pi over 3, 2 pi over 3, then at 4 pi over 3 and at 5 pi over 3, we would get angles that give us a y-coordinate of negative square root 3/2. So all in all, there's 4 angles that satisfy this equation. There's 4 angles that give us either a y-coordinate of positive or negative square root 3/2. And that's all of our solutions on one rotation around that unit circle, or from 0 to 2 pi. So I hope that makes sense. Hope you're seeing really the necessity of changing our double angle into something that relates to what we have already. That's the appropriate choice to make, is something that matches up with what you have. Otherwise, we might be going in circles for a little while if we pick the wrong thing here. So be very careful on what you're picking. Make sure it's matching what you have. All right, let's look at the next one. We got cosine of 2 theta equals cosine of, I forgot the theta. equals cosine of theta. Now, what do you do here? I really want you to think through this on your own. Don't pause the video, but think about what I'm asking you to do. Look at the piece that is difficult to deal with. Hopefully in your head it's the cosine 2 theta. Now, cosine 2 theta, that's a double angle that has 3 different formulas. Which one matches up best with what you have already? Would you want to see sines or would you want to see cosines? Well, if you already have a cosine, you can change this into one of 3 things. You can change it into cosine squared theta minus sine squared theta. You can change it into 1 minus 2 sine squared theta. Or you can change it into 2 cosine squared theta minus 1. Which one matches up with what you have over here? Well, probably not the stuff with sines in it. So maybe I choose the double angle formula for cosine that has to do with cosine, and just cosine. That's going to give us 2 cosine squared theta minus 1. So where do we go from there? Well, at this point, I hope you're noticing the format of this. You got a power 2 cosine, you got a power 1 cosine, you got a constant. This is a really good opportunity for us to factor. So let's get everything on one side and let's see if we can factor this. So we've got things on one side in order. We've kept our first term positive. The first term is the term with the largest power. And so in our case, we want to keep that power 2 cosine, keep that positive. I hope it's making sense that we want to pick the thing that matches what we have. That lets factoring happen a lot easier. Lets a lot of other combined like terms happen. So when we look at this and say, which one do we choose? Oftentimes it's based on what we have outside of that double angle. Like here, we had sine squared. We want to combine some like terms. Pick this up with sine, not cosine. Here we have just a cosine. Pick this up with just cosine and not sine. Now that we have this, this could be an opportunity for a substitution. You could call cosine theta equal to u. You have something raised to the second power, something raised to the first power, and it's the same something. Call that u, or some other dummy variable. So we get 2u squared minus u minus 1. We've talked about substitutions a lot in this series and in past series. It just lets you factor easier. It lets you change things that look hard to factor into things that are easy. So 2u squared minus u minus 1 is pretty easy for us to see that we can factor that. We'd have negative 1, negative 2. Looks like we'd get negative 2 and positive 1. If we want to divide by our a and simplify, you can factor this as 1u minus 1 times 2u plus 1. Or you could just straight up solve this right now. If you change these signs, that will solve your u. So you could put down here u equals positive 1, u equals negative 1/2, and you're done. So if all we're looking for is a solution, not the factoring, you can go right from here. As long as you've divided by your a first, that works. If not, if you like the factoring better, you can do 2u plus 1, 1u minus 1 equals 0. And you can probably see this. 2u plus 1 equals 0 would give you negative 1/2. U minus 1 equals 0 would give you positive 1. We're not done, but we're very close. Remember that we use this substitution here. So what is u really? U is really cosine theta. So if u equals 1, that means cosine theta equals 1. And if u equals negative 1/2, that means cosine theta equals negative 1/2. Could you have just factored from here? Yeah, that's fine. If the substitution is not necessary for you, you could easily factor this as 2 cosine theta plus 1 and cosine theta minus 1. That's fine too. It doesn't really matter. I'm just giving you another option. What isn't optional is solving this the rest of the way. So we take a look at our unit circle. Cosine theta equals 1. So what angle gives you an x-coordinate of 1? That's got to be 0. So cosine theta equals 1 only when theta equals 0. Notice that we don't allow this to get to 2 pi, so it's just at 0. Cosine theta equals negative 1/2 at 2 places, in quadrants 2 and 3. Because cosine is the x-coordinate is negative in quadrants 2 and 3, and will equal an x-coordinate of negative 1/2, I should say, at, let's see, 2 pi over 3 and 4 pi over 3. If you look at your unit circle, we're just finding out where cosine theta equals -1/2. You're going to find 2 pi over 3 and 4 pi over 3. And those are all the solutions on one revolution of the unit circle, or from 0 to 2 pi, that satisfy that equation. Okay, last one. So we have sine of 2 theta equals cosine theta. We really want to change some double angles. They're difficult to deal with when we deal with other things that don't have a double angle. So like when we have sine of 2 theta and cosine theta, the 2 theta makes it very difficult for us to manipulate that. Because if you have different angles, they're hard to combine, they're hard to factor. You can't factor them, you can't pull the 2 out. You can't do anything with a double angle if you have other angles that are not 2 theta. That's why we were changing all the double angles into the appropriate formula. So now when we get sine of 2 theta equals cosine theta, we have to change that sine of 2 theta. Now this is really good news because there's only one formula for a double angle for sine. So sine of 2 theta only equals one thing, and you really have to use it. So you don't have to choose anything. This is only going to equal 2 sine theta cosine theta. For the last time, you don't just need to pull the 2 out. The only way you change arguments in trig functions is with identities. The identity for a double angle for sine says you can change this as long as you do sine of 2 times sine of theta cosine theta. Since there's only one formula, it's the one that we have to use. Now what do? Well, this looks like it could be another factoring issue because I have something with a cosine and I have a cosine over here. So maybe we start getting everything on one side to see if we can factor. Equations usually work that way when you have two different terms with the same function or the same variable, or one's squared and one's not. Let's see if factoring works. So let's get everything on one side. One thing to be cautious of, I've seen it from time to time, it doesn't happen often, but don't start dividing both sides by something to eliminate it, because what happens is you'll start to eliminate some of your solutions. So if we divided both sides by cosine theta, sure, it would cancel out, but you're going to eliminate some solutions, and you're also technically divided by something that could equal 0. And so you do run into some domain issues there. So don't do that. Get everything on one side and see if you can factor it. So if we have 2 sine theta cosine theta minus cosine theta, hey, you've got 2 terms. They both have cosine theta in them. Let's factor that out. Now that we've factored, when we have a 0, you can use a 0 product property for this. So because you have 2 pieces multiplied together equals 0, either cosine theta equals 0 or 2 sine theta minus 1 equals 0. Now that's already solved. We're just going to have to find the angle that gives us an x-coordinate of 0. Here we'll add 1 and divide by 2. We'll isolate that sine theta. And on the interval from 0 to 2 pi, the only place where we have an x-coordinate of 0 is at pi over 2 and at 3 pi over 2. So we hit x-coordinate of 0 at pi over 2, and then again at 3 pi over 2. So this has 2 solutions. The only place where we have a y-coordinate of 1/2 on the unit circle happens at pi over 6 and at 5 pi over 6. So we'd certainly want our unit circle handy to be able to find out if cosine theta equals 0, we're really just asking what angle gives us an x-coordinate, because cosine is the x-coordinate on a unit circle of 0, and that's pi over 2, 3 pi over 2. What angle on a unit circle gives us a y-coordinate of 1/2, because sine theta is the y-coordinate on a unit circle. That happens at pi over 6 and 5 pi over 6. So I hope this has made sense. I hope I've walked you through enough examples to illustrate the use of a double angle and a half angle formula, when to use them, what they look like, especially identities and some of these equations on how to do that. These can get pretty confusing, but remember that the double angle piece is typically the piece we want to get rid of. Usually, not always, but usually. With cosine, we just want to pick the right one that matches the rest of our stuff, either to combine like terms or that makes factoring possible. So I hope that helps you. Hope you've enjoyed the videos, and we'll see you next time for a couple different identities that we'll make up.